Hello and welcome. Have you ever just stopped and wondered why things move the way they do? You know, why does a ball stop rolling? And what does it really take to get something, well, going? For ages, this was a huge, huge puzzle. But lucky for us, brilliant people like Sir Isaac Newton basically gave us the rule book for the universe. So let's dive right in and unpack the amazing secrets of force and motion. All right, so here's our plan for today. We're going to start with the old question that had ancient thinkers totally stumped. Then, we'll uncover the real reason things move and walk through Newton's three legendary laws, one by one. And to wrap it all up, we'll see how these cosmic rules are literally playing out all around you every single day. So, let's kick things off with that big puzzle. The one that bothered scientists and philosophers for centuries. Why on earth do things stop moving? I mean, really think about it for a second. You give a ball a good, solid push across the ground, it rolls for a bit, and then it just slows down and stops. This super simple, everyday thing we've all seen a million times led to an idea that ruled science for thousands of years. The only problem? It was completely wrong. For a very, very long time, people believed that the natural, default state for everything was just to be still, to be at rest. And you can kind of see why, right? It just made sense. If you wanted to keep something moving, you had to keep pushing it. So from that point of view, motion was something you had to constantly cause, while stopping was just an object going back to its normal, lazy state. So what was the big aha moment? The answer, the real breakthrough, was a concept that honestly changed everything: unbalanced forces. This is where brilliant minds like Galileo and Newton came in and totally rewrote our understanding of the universe, finally cracking that ancient puzzle. So first things first, what even is a force? At its very core, it's just a push or a pull. That's it. But here's the really cool part. We can't actually see a force. You can't taste it, you can't touch it directly. We only ever see or feel what it does to things. And what are those effects? Well, a force can get something that's standing still to start moving. It can bring a moving object to a complete halt. It can change the direction an object is headed. Oh, and it can even change the shape or size of an object, like when you squeeze a stress ball. Okay, now this is the most important idea to get. When all forces acting on an object are balanced, think of a tug of war where both teams are pulling with the exact same strength. Nothing changes. The object just stays put. But when the forces become unbalanced, when one push is stronger than the force pushing back, that's when the magic happens. That's when you get a change in motion. That's when you get acceleration. Imagine you're trying to push a really heavy box across the floor. You give it a little push, but the friction between the box and the floor is pushing back just as hard. The forces are balanced, so nothing. You push a bit harder, and friction rises up to meet you. Still balanced, still nothing. But then, you give it one really strong shove. Finally, your push is stronger than the friction. The forces are unbalanced, and there it goes. The box starts to slide. This idea of unbalanced forces leads us perfectly into Newton's first law, which is all about something called inertia. I like to call it the universe's law of just keep doing what you're already doing. Now, that's the official textbook definition. Basically, it means an object that's not moving will stay not moving, and an object that is moving will keep moving at the same speed, in the same direction, forever, unless some unbalanced force comes along and messes things up. This was a revolutionary idea that completely flipped that old belief about rest being the natural state. And this stubborn tendency to resist change, that's what we call inertia. The most important thing to remember here is that inertia is all about mass. The more stuff an object has, the more it resists being pushed around. It's exactly why it's way harder to get a car moving than it is to push a bicycle. The car has so much more mass, and because of that, so much more inertia. A really fun way to see this in action is with a stack of carom coins. So you have a neat stack of coins. Now, if you take a striker and give that very bottom coin a sharp, fast hit, what happens? That bottom coin just shoots out from under the pile, while the rest of the stack just kind of drops straight down. Why? Inertia. The coins on top resisted that sudden change. They wanted to stay at rest even when their support was yanked away. Okay, so if the first law tells us what happens, the second law is all about how much. This is where Newton gives us the actual math to figure out the relationship between force, mass, and acceleration. The three key players in this law are force, which is our push or pull, mass, which is how much inertia something has, and acceleration, which is just any change in an object's speed or direction. And they all come together in one of the most iconic equations in all of physics, F equals ma. What this tells us is that the amount of force you need is equal to the object's mass multiplied by how fast you want it to accelerate. To put it simply, if you want to make a really heavy object speed up really fast, you're going to need a whole lot of force.
All right, moving on to Newton's third law. My favorite way to think about this one is simple. You can't touch without being touched.
I'm pretty sure you've heard this one before. To every action, there is an equal and opposite reaction. What this really means is that forces never, ever show up alone. They always come in pairs. Now, here's the part that can be a little tricky. If the forces are equal and opposite, why don't they just cancel each other out? Well, the key is that the action and reaction forces are acting on two different objects. If you push on a wall, that's the action. The wall pushing back on your hand is the reaction. Since the forces are on different things, they don't cancel, and motion can still happen. And once you look for it, you see this everywhere. When you walk, your foot pushes the ground backward. That's the action. The ground then pushes your foot forward. That's the reaction that actually moves you. When a gun is fired, it pushes the bullet forward and the bullet pushes the gun backward. That's recoil. Even a sailor jumping off a boat, as he jumps forward, he's actually pushing the boat backward. So after all that, let's bring it back home. How do these big cosmic laws actually show up in your day-to-day life? Well, once you start looking, you realize they are absolutely everywhere. Newton's first law, inertia, that's the entire reason we wear seatbelts. If your car stops suddenly, your body wants to keep moving forward. The seatbelt provides that crucial unbalanced force to stop you safely. The second law, F equals ma, that's why pushing a full shopping cart takes so much more effort than an empty one. More mass needs more force. And the third law, that's literally how we get to space. Rockets push hot gas down with incredible force, and the equal and opposite reaction pushes the rocket up. Amazing, right? And that brings us to a final thought, a classic little brain teaser to leave you with. If every single action has an equal and opposite reaction, how does anything ever really move at all? The answer is hidden in what we've just talked about, but it's a fantastic puzzle to think about. Thanks so much for joining me today, and keep looking for the physics in your world.